Theorem 4.3 is an analog to what we've done with 2x2 matrices. It says the determinant of an n by n matrix is a linear function of each row when the remaining rows are held fixed. So explicitly, if a1 through an and v are all row vectors in Fn, and k is a scalar, then you can explicitly say this as the determinant of this matrix is equal to the determinant of this matrix plus k times the determinant of this matrix. Remember, we're just describing the matrices in terms of their rows. So we're going to do a proof by induction, which is fairly typical with determinants, since determinants are defined by induction. And maybe I should say proof by induction on n, right? So if n equals 1, think about it. Let's see what would happen if you only had one row. Well, then the determinant of, I guess it would be just a single entry, a11 plus k. V would be a vector of length 1, so that's just a scalar. The determinant, the definition of determinant on a one-dimensional vector is just a11 plus k. Maybe we should put a 1 there just to indicate this is just a single entry, v1, right? That's what happens in one dimension. But of course, this is just the determinant in one dimension plus k, a scalar, times the determinant again in one dimension. So it's a little silly, but clearly it holds, okay? Now, for n greater than or equal to 2, assume the statement holds. For n minus 1. So we've got this sort of statement above for n minus 1. Let A be an n by n matrix with rows a1 to an, and let V be another vector in Fn, another row vector, basically. So then, probably for notation, let's call, let's see, what should we call? Call B the vector that is A1 all the way down to A, R minus 1V, AR plus 1 all the way down to AN. So this is B, this is A. And we're going to say C is going to be, we're just defining it to be that. It'll just shorten up our proof maybe a little bit, having shorthand for these. R minus 1, let's see, AR plus KV, AR plus 1, AN. Okay, so for notation, we'll just give those shorthands. Okay, so now here, the proof looks a little different depending on what R is, because remember, the definition of determinant is running across that top row. So if R equals 1, in other words, this top row is where you have this thing happening, okay, then here's what happens. The determinant of C equals -1 to the 1 plus j, and let's think about what happens if this right here is in the very top entry, right? Well then, what are those entries? Those entries are a1j plus k v j, right? A1j minor. Determinant of A1j minor, right? So that's what we have there. And then, of course, these are all just scalars. So you could totally break this apart here. You could just write that as -1 to the 1 plus j A1j det 1j minor plus, and every single one of these has a k, -1, 1 plus j vj det A1j. Right? So we've got that just fine. And then just think about what this is. Well, this right here is exactly the definition of the determinant of A, right? And what's this? This is K, and if you put the V's in there, that's just the definition of B, of the determinant of B. So you proved it true just pretty straightforwardly there. You didn't even have to borrow the induction here. But if r is greater than 1, then we're not actually having this happen in our coefficients, right? What's happening here is the determinant of C is equal to, again, -1, 1 plus j. And this is a fairly common convention. Every single one of these I could write j equals 1 to n, every single sum. But as long as there's no ambiguity, every single sum on the whole page goes 1 to n. Often we omit writing that. We could say aij det c1j minor, right? That's just the definition of determinant. But then what is this? Well, that is an n-1 by n-1 matrix, right? So we can use induction on this. That's so that equals -1, 1 plus j, A1j. And then remember, we just made the inductive claim that that's the determinant of A1j minor plus k times the determinant of B1j minor, right? And so, of course, you could split this up. As you might expect, it's a sum with two pieces there. So -1 to the 1 plus j aij det aij minor. Well, what's that? That's the definition of the determinant of A plus this k can actually come out in front, right? And then you have -1 to the 1 plus j aij det bij minor. And notice aij, right, that's the top row in all of the matrices if r is greater than 1. So that's why there's no issue with calling all of those A1j, A1j, A1j. So this is just determinant of A plus k determinant of B, therefore true by induction.